In 1942, some of the world's best scientists seriously worried that detonating a nuclear bomb might ignite the atmosphere and end all life on Earth. They did it anyway. Decades later, many scientists warned that switching on the Large Hadron Collider might create a black hole, one that could consume the planet. They did it anyway. But there is one experiment so extreme, so dangerous in principle, that scientists publicly said it should never be attempted. And then, they did it anyway. We start when the world was already on fire. It was 1945. The Second World War was reaching its final, brutal act. Europe lay in ruins. The Pacific War was grinding on, and the American planners were facing a choice with no clean answer. Invade Japan conventionally and accept casualty estimates that ran into the hundreds of thousands or even 1 million lives, or force a surrender by unleashing a weapon with destructive power the likes the world had never seen. It was, and still is, a moral question with no settled resolution. But before any of that, there was another question. As the Manhattan Project prepared to test the first atomic bomb, a concern was raised by physicists working on the weapon itself. Not fringe voices, not panic speculation, serious scientists. They asked whether detonating a nuclear bomb might ignite the nitrogen in Earth's atmosphere, triggering a runaway reaction and ending all life on the planet. The calculations were incomplete, the physics was new, and absolute certainty was impossible. The risk was judged to be extremely small, not zero, small. And under the pressure of war, with the cost of inaction measured in cities and lives, they decided that was enough. On July 16, 1945, the Trinity test went ahead. The atmosphere did not ignite. The world did not end. But a line had been crossed. From that moment on, humanity accepted something new, that even when the stakes are absolute, decisions are still made under uncertainty. In December 1942, years before Trinity, physicists were attempting something entirely new. Not a bomb, not a weapon. A self-sustaining nuclear chain reaction. If it worked, it would prove that nuclear energy could be released slowly, predictably, and, in theory, controlled. If it didn't, it could run away. No one had ever done this before. No one knew for certain where the tipping point lay. Too little material and nothing would happen. Too much and the reaction could accelerate beyond control. So you'd expect a test this dangerous to happen somewhere remote, in the desert, like Trinity, or at least far from major centres of population. Yeah, that didn't happen. Instead, the experiment took place beneath a football stadium at the University of Chicago. No containment dome, no remote shutdown system. The reactor was controlled by neutron-absorbing rods. As long as the rods stayed in place, the reaction slowed. If they were pulled too far, the reaction would accelerate. Most of the rods were adjusted by hand, carefully, gradually. And as a final precaution, one control rod was tied to a rope. If the reaction began to run away, the plan was simple. Cut the rope, drop the rod, stop the reaction. Which is why one man stood by with an axe. Yes, you heard that correctly. The safety system for the world's first controlled nuclear experiment was a man with an axe and a rope. The reactor went critical. The chain reaction sustained itself. And then it was brought under control. It worked. And with that success, something subtle changed. Not because the danger was gone, but because it had been survived. From that moment on, probably safe started to feel safe enough. And that state of mind is very much present in our next example of high-stakes science. Not all threats come from physics. In our next example, the danger wasn't explosive, it was biological. By the 1970s, scientists had learned how to cut and recombine DNA, moving genes between organisms, rewriting the instructions of life itself. What is now called genetic engineering. For the first time, evolution was no longer blind. It could be guided, directed, accelerated. And that made people uncomfortable. Not because the science was sloppy, but because the consequences were open-ended. Engineered organisms might escape the laboratory, they might spread, they might persist. Once released, a living system doesn't explode, it reproduces, and it doesn't ask permission. Earth's entire biosphere was suddenly at risk of contamination, and maybe even annihilation. The scientists working on it knew this all too well. So they paused, for a while. Conferences were held, guidelines were written, warnings were issued. Not because disaster had occurred, but because no one could say what wouldn't happen. And then the pause ended. The research resumed, under rules, under oversight, under the belief that the risks were now understood well enough. Not eliminated, managed. Life was rewritten, organisms were engineered. The stakes, no matter how small the probability, were life itself, and the boundary was still crossed. The warnings were heard, the risks were acknowledged, and they did it anyway. In 2008, humanity finished building the most complex machine it had ever created, the Large Hadron Collider. A 17-mile ring of superconducting magnets buried 300 feet beneath the Swiss-French border, designed to smash particles together at near light speed and recreate conditions not seen since the birth of the universe. The goal was to probe the deepest structure of reality itself, to understand why matter has mass, to find what became known as the Higgs boson. But as engineers prepared to fire the first beam, a very different idea escaped the lab. The fear was microscopic black holes. Critics argued that smashing protons together at unprecedented energies might create a point of extreme density, a tiny gravitational object that could sink to the centre of the Earth and consume the planet from the inside out. It sounded absurd, and yet it was consistent with known physics. The concern didn't stay online, it reached the courts. A federal lawsuit was filed to prevent the machine from being switched on. The lawsuit reached a federal court in Hawaii. The judges didn't rule on whether the fears were right or wrong. They dismissed it for a colder reason. The experiment was already beyond their jurisdiction, buried beneath Europe and untouchable by US law. For a moment, humanity openly asked whether curiosity had finally outrun caution. Physicists responded with mathematics. They pointed to Hawking radiation, a mechanism by which tiny black holes, if they formed at all, would evaporate almost instantly. According to the equations, they would vanish before consuming even a single atom. The risk was judged to be vanishingly small, not zero, small. There was no absolute guarantee, only probability, theory, and confidence. On September 10th, 2008, the switch was flipped. The world did not end, but once again the pattern held. Smart people raised the concern, other smart people calculated the risk, and they did it anyway. We end on something quieter and far more dangerous. If the atomic bomb threatened the air, and the Large Hadron Collider threatened the ground, the relativistic Heavy Ion Collider threatened something deeper. Not the planet, not even space. It threatened the rules of the cosmos itself. RHIC wasn't built to smash simple particles together. It didn't fire lone protons like bullets. It fired gold. And this matters. Whole atomic nuclei, heavy, crowded, complex, stripped bare and hurled at one another at nearly the speed of light. When they collided, they didn't just break apart, they melted. For a fraction of a second, matter itself collapsed into a primordial fireball, a quark-gluon plasma, a state of existence that hadn't naturally occurred since the first microseconds after the Big Bang. This wasn't fusion, it wasn't fission, it was matter forgetting what it was supposed to be. For an instant, humans created the hottest substance ever produced on Earth, thousands of times hotter than the core of the Sun, recreating conditions the universe hadn't allowed for nearly 14 billion years. But some physicists realised this extreme environment could, in principle, create something called a strangelet. In ordinary matter, quarks come in two types, up and down, but there is a third, heavier type called a strange quark. Usually, these are unstable and vanish almost instantly. However, the strange matter hypothesis suggests that if you get enough of them together, they could become the most stable substance in the universe. So stable, in fact, that strange matter becomes infectious. If a single stable strangelet were created in a lab, it wouldn't just sit there. Because it is more stable than ordinary atoms, it would act like a cosmic catalyst. Any ordinary nucleus it touched could be forced to convert, its up and down quarks collapsing into strange quarks to match the newcomer. It would be a biological plague at the subatomic level. If a strangelet fell into the floor of the lab, it could begin converting the Earth's atoms into strange matter. The chain reaction would be unstoppable. Within hours, the entire planet might be converted into a single, hyperdense sphere of strange soup, no larger than a football stadium. But the destruction wouldn't stop at Earth. Because this matter could be interpreted as the true ground state of the universe, the infection could theoretically spread to anything it touched. It could travel through the void, converting every moon, every planet, and every star it encountered. It wouldn't just end life, it would overwrite the very recipe for the universe, an infectious agent of reality itself, for which the universe has no immunity. The risk was deemed so small it was almost unmeasurable, 1 in tens of millions. Scientists pointed to the stars for reassurance. For billions of years, cosmic rays have been slamming into the moon with more power than any collider. If those collisions could create world-ending strangelets, the moon would already be gone. But there was a flaw in the logic. Cosmic rays are mostly single protons, travelling alone. The RHIC was different. It was smashing gold, heavy, complex, and packed with neutrons. And while a cosmic ray might create a strangelet that screams through a planet at near light speed and out the other side, a collider could, in principle, create one that is still. A slow, heavy drop of strange matter, not passing through the floor, but sinking into it. The lunar defense wasn't a perfect shield, it was an educated guess. And yet, with the recipe for the universe on the line, they did it anyway. Igniting the whole atmosphere would have been reckless. Creating a black hole that consumed the Earth would have been negligent. But altering the universe at a fundamental level, well, that would have been borderline criminal. And yet, in every case we've looked at, the pattern is the same. The risks were known. The warnings were raised, the debates were real. But certainty never arrived. Instead, there was probability, confidence, and the belief that knowing was worth the risk. This isn't a story about reckless scientists or mad geniuses. It's a story about how progress actually happens. At the edge of knowledge, someone always has to decide when probably safe is safe enough. Thanks for watching. See you next time.